I'm going to talk to you today about designing molecules to make materials that can efficiently harvest sunlight for solar fuels production. So in the background here, we have an image of nanofibers. These fibers are incredibly small. So the scale bar on the bottom right is 1 micron. The width of a human hair is somewhere between 20 to 100 microns. So these are hundreds of times smaller than the human hair. These are incredibly small fibers. So today I want to talk to you about how we make these fibers and what kind of big problems we can solve using such small fibers. One of those problems is energy. As many of you probably know, the global energy demand is sharply rising and is expected to at least double by the year 2050. Also, as Peter alluded to earlier, the rise in CO2 emissions is causing massive climate changes which could have very serious consequences. So we need to find a new and sustainable form of fuel production. And one place to look is the sun. The sun delivers a huge amount of energy to the Earth every day. Some estimates say that we'd only need to harvest about 0.2% of the energy that's hitting the Earth's surface to power our entire planet. So how do people think about harvesting this energy? Well, one way is solar panels, or photovoltaics, and Suzanne is using those in her research. And these are good, but they work by converting solar light directly into electricity. And so you have to use that electricity right away or store it in a battery. And this isn't good for certain long-range applications, such as maybe flying an airplane halfway across the world. For this, we need a denser form of energy storage, and that would be fuel. So we can think about doing this through something called solar fuels or artificial photosynthesis, in which we mimic the plant's ability to harvest sunlight and convert CO2 into fuels which can be stored. So as a chemist, the way we think about this in a molecular system is we have a molecule that we'll call PS as a photosensitizer. This is the molecule that will absorb visible light. And when we excite it, when we shine light on it, it gets excited to a high energy state, and it can transfer the energy that it's absorbed to a catalyst which can turn CO2 into fuel. So in our lab, we are focused on the photosensitizer part and developing inexpensive and efficient photosensitizers. So specifically, we do that through a process called self-assembly. So normally, when you take a solid and you dissolve it in solution, you just get a dispersion of molecules that's randomly solvated, and there's no particular order to them. But in self-assembly, we can design molecules such that when we dissolve them in solution, they spontaneously order and make long-range assemblies of molecules. And these assemblies can have really interesting properties that we can use. So how do we design molecules to assemble in this way? One way is through something called pi-pi stacking, where essentially molecules, electron clouds, which are shown in the top left there, can interact with each other positively and lead to extended stacks of molecules. Another way is through the hydrophobic effect, and this is actually how soap works. So in soap, you have a hydrophilic and a hydrophobic portion. The hydrophobic part traps all the dirt and oil and other hydrophobic things, and the hydrophilic part allows it to be solubilized and go down the drain. Well, here we take a molecule that has a hydrophobic region and then the hydrophilic or water-loving region, and when we dissolve it in water, the molecules order such that the hydrophobic parts stick together away from the water, and the hydrophilic parts face towards water. So in our lab, we are interested in taking this approach for, as I said before, for photosensitizers, for visible light harvesters. So we choose an organic dye molecule, and these actually have some of the pi stacking propensities that I mentioned earlier. But by themselves, they're not very good at transferring the energy that they absorb from light to catalysts. So it's not great. So how do we improve this? Well, we attach a hydrophilic group to the molecule, so then when we dissolve it in aqueous solution, it assembles into an organic dye assembly. And it turns out that this assembly is much better at transferring energy to a catalyst, which can then make fuel. So additionally, another advantage of these molecules is that when they assemble to make these extended structures, as we showed before, they make these fibers, and I kind of picture that in a schematic on the right, but we also have a real picture, which is in the bottom right, that's taken from the first image. And these actually can trap the solvent and make it gel, which is shown in the middle here. So here we're going kind of So we talked a little bit before about building materials. So this is actually a bottom-up approach to building materials because we're going from a single molecule, which then self-assembles to make these nanostructures, which then coalesce and create a gel, which is then a material which you can handle and has mechanical properties on the macro scale. So in our lab, we've been able to eliminate these gels in the presence of CO2 and convert CO2 into carbon monoxide, which is not quite a solar fuel, but is one step closer. You can take carbon monoxide and hydrogen and make hydrocarbons, plastics, fuels, or you can continue to reduce it through other processes to methanol, which you could actually put into a car or other sort of fuel burning device. So in conclusion, we can rationally design molecules through certain chemical motifs to self-assemble into well-defined structures like these nanofibers, which lead to functional materials that can solve some of the major problems that we're facing today. So with that, I'd like to thank my research group, the Stoop Lab, RSG, and my funding source. And thank you for listening.